Good afternoon, Sunday afternoon, about 1:58. And what is ongoing has been the discussion of the differential and the calculus that lives above arithmetic, that lives above algebra, that lives above, I don't know how you put it, operator calculus, where it results that what's relevant and most profound about the operator calculus is it's basically any kind of application of things. It results as after model theory, up and down from model theory, that basically what a model represents is any kind of structure that maintains, embeds, or embodies all the structural relations of any other given structure. So you say it can be a model of it. And if everything that's so, according to any kind of transition or act in one model is the same in the other model, you say that one model is the other. And so then there are partial models and full models and supermodels and submodels and the proper of those. And they basically represent, when we talk about numbers, that they're models of objects with arithmetic and models of objects with algebras. Models of objects for analysis and these kinds of things. And that similarly, when we try to describe that, well, what about all the objects of reason and those being a monist theory, a single theory, a monist theory of things, how can there be a pure model of all these things? Well, that's exactly kind of the import of the technical philosophy. How can there be something rather than nothing? And if so, what is it and how is it so truly? How are all the question words answered about it that make it so that thus what so results as examining the model or exercising the model, that it works out that it's one true theory. And so when we talked a little bit before about the logical and the non-logical or properly logical. That the logical is basically that's which is represented by the purely logical applications of things. Inference, causality, lack thereof, contradiction, lack thereof, and identity, equality, and tautology, those being for many people the same kind of thing, equals. But for something like extensionality, that we can say this model models the other model, and so you can equate that what's one so in one is so in the other one, that extensionally they're the same, when you couldn't really compare them either way. If you had a bucket of apples and a bucket of oranges, you could model that you place one at a time in each, and then you know how many is in one, and you can model counting the one by counting the other one. That extensionally, via this abstraction, what results that the count of one is the same as the count as the other one of the act of counting, given that it has a number and that it makes a count or has made a count. That these are the kinds of things that get into intentionality, which is the thing is unique and exists, and it is its sole value, its sole name, its sole thing. That the extensionality is any application of an abstraction of things that results, you can say things are the same. Kind of like in this manner. In a lot of the talks, there's been talk about algebra and arithmetic and the objects of the number spaces. That there are number spaces, that there are points and spaces in geometry, that there are numbers in number theory, and that geometrical objects are primary in geometry and numbers are primary in geometry, and that there's a guy named Thomas Hardy has a great book called Pure Mathematics, and he puts them together, where he says, for example, that in our algebra, how we build things after abstract algebra for foundations in our descriptive set theory, first there's built up to integers, and that often follows an axiomatization. They're often called Peano's integers for Giuseppe Peano, who also has a theory of infinitesimals, but that's left right out because it's non-standard. But then here in the standard, then after the integers are built to ratios of numbers. These can form a field called the rational numbers, and any number that can be a ratio of two integers is the rational numbers. And as was discussed here, there's algebraic numbers above those, any solutions of polynomial equations, or what can be written as a continued fraction, where there are various ways to write numbers. There's a solution of polynomial equations as a usual sequence of digits to the left and right of the radix or decimal point, as continued fractions, as infinite series or sum, that then for the next step in what are these numbers so built, the real numbers are the completion of the complete ordered field, as from the ordered field, the rationals, that is axiomatized, again, another stipulation, another decision, another opinion, which is arguable, that makes it so that there are these real numbers from 0 to infinity, or from 0 to 1. A lot of times it's easier then to deal with everything between 0 and 1, or just the positive numbers. A lot of times algebra will start saying, well, first let's get the real number line so we won't have to leave that out later, and we can use the same diagram all the way along, and there's a positive and the negative numbers. Whereas other times, these numbers like piano's integers, first you define successor, n and n plus 1, that 0 exists and then n plus 1 exists. That via induction, each of these things is called an integer. Then there's another axiomatization maker, these field operations that make for the field, that there's addition and multiplication, and then we get into Peano and Pressburger, that Peano makes for first order multiplication, or second order multiplication, first order addition, and Peano kind of has them together because he breaks down multiplication and makes it like so. There's a lot that goes into these derivations that also can be achieved via other derivations, other means. So just considering the non-negative or positive numbers, where the non-negative includes 0 and the positive doesn't include 0, there's a panel that really gets into a lot of the algebraic geometry, and they call themselves Bourbaki, and Bourbaki was Bourbaki, and they were a bunch of French mathematicians in the 20s and 30s, and so they set out to help describe algebraic geometry about number theory. So they're largely number theorists, but they work in what they like to call a field called algebraic geometry. And so they also introduced the word strictly. Like when they say negative, they mean strictly negative. So they might include 0 in negative or include 0 in positive. So when they furthermore just say strictly positive to mean non-zero and non-negative, where usually we just say non-negative when we want to exclude 0, and positive when, non-negative when we want to include 0, and positive when it's meant the open interval on the left, not including 0, but so bounded, and then it's the infinity above. There's no bound. And then we get into the various number systems that, before completing this bit about the extensionality and intentionality of the real numbers, there's various number systems that have a point at infinity, and various ones that do not. It's called a projective point at infinity. It's called not to scale. The label for the rightmost side of the diagram, if not anywhere actually on the diagram according to scale. But then that it means infinity. It means a particularly large quantity. That it often reflects, what it means is that it reflects a process, that there's more and more and more with respect to any bounded quantity for an upper and lower bound, usually to the left and right, or right and left, respectively, that it is such a thing. So when we talked about the notion of the field being compact the other day, it is not. But if it has a point in infinity, it's called a one-point compactification. That infinity added there makes it so that then there's relations to these kinds of differential quantities we've been talking about, reading about Banach spaces and the compact of these otherwise metrified normal linear spaces. That then makes for why it does or doesn't become degenerate at that point at infinity, the point in perspective at infinity, the point at infinity, why or why not that is so. For geometry's sake, and what it means that otherwise there are straight lines and there are right angles and this kind of thing in integer lattices. So going back to the real numbers, and now that they've been built up from the integers, the rationals, the real numbers, when you consider 1.0, the real number, and 1 over 1, the rational number, and 1, the integer, via extensionality, they're the same. It so happens that besides just defining an infinite sequence of integers and saying they're the integers, because that's just cases for induction, they don't maintain constancy between them so necessarily. It has to be built above. There's something for them to build into. It sort of works out that the piano's numbers are incomplete for a lot of people's definitions, because all they really provide is an inductive set. And then that, as for the ordinals, as for the numbering of things, it provides an index, provides an ordering. But as far as it making a lattice, is that constant differences and differences in multiples also have to be built up. So it gets to why, that though the integers are like the numbers, the whole numbers, the counting numbers, all these are names for the integers, although not necessarily the negative integers. The natural numbers are the non-negative integers. And then they also admit an ordinal representation, that they have infinity, that they go to it regularly, that they divide so regularly. That's how they establish making that they're inverses, and also the additivity and transitivity of more than the pairwise, which is only this and the next one, x plus 1. This and some further higher order sum of those, sum of multiply many, that has to be built up and built back down in these numbers. And so it results that for some people, infinity is a very, very natural part of the natural numbers. In set theory, it's called omega, and it's said that omega is an ordinal and it contains all the numbers. Where the very definition for a lot of people of the von Neumann ordinal is just a set that contains a previous ordinal, which nest and nest and nest and implement these Peano successors, n plus 1. So some might argue that it's a very simple matter of deduction that infinity exists. And others need not make it so, because they can instead establish for all the unbounded cases, for each one you just have to count up higher and higher. And if you need to maintain accumulating sums, then it so exists all these axiom schema of the higher order, that it's like not only can you apply this axiom and make a statement in the theory, but you have to keep up the rest of the schema, the higher order. That is so that at least one of the axioms of Zermelo-Fraenkel set theory is a schema. And it's necessarily unbounded. But at the same time, everything in Z of set theory is pairwise, because otherwise you can really directly arrive at that. You can take an infinite union of things and arrive at constant infinitesimals between 0 and 1, which are not standard real numbers. And that's very confusing to people, because their intentionality and extensionality, they would not otherwise keep track of that. That's not only non-standard real numbers, but the function to arrive at it from the integers is not a Cartesian function. And so that otherwise in these axiom schema and the axioms and the definitions of things, it works out that there needs to be basically two separate worlds for these two definitions of continuity. One for line continuity, one for field continuity. That line continuity is this between 0 and 1, time goes from 0 to 1. It's infinitely divisible. And each point on that line, according to Thomas Hardy, is a point on the line, and it's also a real numbers value. And furthermore, the points on that line are contiguous, and each one has a next on it, just like the integers have a next, that fitting it back down and into this unit makes a next. That it's almost to be argued whether or not what is standard the complete order field is so, especially because it helps bring in all the algebra of words and all this higher level stuff, and it makes for the algebra after Galois and the group theory and the ring theory and all these things with regards to inverses and the symmetrical and reciprocals and the identities, and that a linear course, and they hold up together. And there's nothing wrong with that at all, except in the sense that it's not complete and it's not sufficient to relate all the relations in real numbers this way, that there are real relations in real numbers above and about the definitions of continuous functions, which are the usual milieu of how we apply these things and build these things, that are just the line continuums, Aristotle's continuum, iota values, the equivalency functions range, the natural integers to the unit intervals equivalency functions range, or sweep. So some can argue that you can arrive from first principles if you just kind of take a left turn, or don't take the left turn, as it were, arrive at that. That's built first before you even have negative numbers. It's simply the non-integer part of a number. It completes them with regards to the vector space of the real numbers, the Euclidean plane, and these other things that it basically represents what's called line drawing. In the Euclidean geometry, there are two tools of classical constructions. There's the compass, which can maintain a fixed distance and a fixed point on one side, and then it can make a mark on the other side, or a mark when it crosses the line variously. Some people have compasses that draw a trace. Others, there's just like you can hold one end as a hinge and swing it around to where it meets some other line. So the compass, and then the edge is that then you can connect 2 points and draw a line between them. Then this line drawing is an act. So when we think about the classical constructions geometry, it's pretty much always included. It's not included in geometry necessarily a measure or meter. The edge has no marks on it. The compass you cannot really pick up a compass and you cannot pick up a compass and have it not change size. Every time you pick up the compass, it's closed. Though, as a matter of fact, once you have a particular setting on the compass, its arms, you can leave it the same distance and trace the same things by some measuring it. But otherwise, it has to be built from laying it down on marks and then swiveling it, making another mark. So anyways, these tools of classical constructions were very critical, because what they were is they're available for the tools of proof, because then everybody could have them, and also they were able to have the geometry after Euclid's geometry. Kind of like a Bourbaki was a panel on French algebraic geometers and trying to figure out for Grothendieck universes and points in infinity, and various questions about analysis, standard and non-standard, and about various questions in number theory and various conjectures in number theory that don't necessarily have true or false as conjectures, true or false. They may be even independent standard number theory. The Euclid, of course, was the panel of the geometers in ancient Greece. And so it so became that Euclid was the most published work after the Bible, or that in all of recorded history is since 0 AD, the most published work is the Bible or the Old New Testament, and the second was Euclid's Elements. Now, at some point in time in the 20th century, that might have flipped over because, for example, it may be so that the People's Republic of China printed billions of copies of Mao Zedong's Little Red Book. That's fine. It's just a matter of fact thing. But over time, amortized for time, it's Euclid's Elements. And in the Elements, he gives a bunch of axioms. He says you don't have to start from nothing. You don't have to figure out all this through analytical deduction to arrive at line drawing and then figure out that these tools result as reflecting some Plato's ideals of the spiral space-filling curve. Here is a compass and here's an edge. That these things are put together. Now there's some other tools that kind of go along with it, and that's basically some pegs and a loop of string, where it's possible that maybe the loop of string is adjustable and the pegs are adjustable vis-a-vis their marks on the page, and that you can connect 2 marks with a line, or that you can put a compasses on 2 marks and then draw to that intersects another line, keeping the same width of the compass, implementing the measure stick, that you basically have to draw a measure stick if you want to use one to build things in geometry. So all these classical constructions then work up, how figures and diagrams can be made, and they can help represent things in proportion and ratio. And they establish matters of projective and perspective, those being very complementary things that comprise to fill something together as a whole. Now, while that is so, there are some things that these methods of exhaustion can accomplish using classical constructions. It's kind of like, as we've been talking about, the numerical methods that are approximations, they're essentially methods of exhaustion that result close approximations as they begin and closer as they continue. So, for example, circumscribing or inscribing in a circle, in a square, or any polygon in a circle, or about a circle, it's possible to get closer and closer from the inside and closer from the outside. What it results the area of the circle. And so it's something that when there's some questions about how it's arrived at these things, then when we get to some things that we're like squaring the circle, how can you compute a circle with the same area as a given square? That is basically shown impossible in exhaustion from these classical constructions and their methods in the pairwise. Just as we were talking about before, in the pairwise versus the infinite union, also called the illative or the univalent these days, where modern theories like commodity type theory and the illative is say, well, let's go ahead and just put this on top of the pairwise standard theory so we can have one without really addressing that it breaks itself. That these pairwise classical constructions provide what they do complete and what for them is also closed forms. And what they attain to, that the limit exists, the methods of exhaustion are the same things as the means of the limit since antiquity, and that's for like segments of circle or the tautochrone, or which is like under the same time it sweeps the same area while it's a curve and not a straight line, and these kinds of things. Gets into that these are the critical and fundamental tools, and that there are certain challenges to it, like squaring the circle, that aren't met because it would take infinitely many steps. Yet, in the unbounded, it attains to that. You can get as close as you need. And the whole theory of asymptotics and approximations and modeling and putting bounds on the error terms is all about how close can we get given how far we can go. And then, of course, modern methods of analysis, the calculus, and it was called for a long time the infinitesimal analysis, but it's called real analysis, and differential systems are all called dynamical modeling these days. That those are closed forms, and so it's key to figure those out, and then for that, these different fields and their different applications and their different milieu, to figure out how to figure out methods, analytical methods, numerical methods, approximations, closed forms, technique, that, for example, work in some cases and make closed forms, but they have a general case to work it out, or they have a general case for anything, but particular forms are difficult or ambiguous, or that they have various cases where they can close otherwise what are intractable or unavailable forms, extensions or restrictions, and these models of things to other things structurally. That this kind of thing is why, when there's only a limited time to teach people mathematics and a limited amount of time to disseminate studies and teachings of mathematics, and a limited window when those curricula are sensible, and that people have enough time and enough dedicated time to give to them, that it can work out that it becomes a common endeavor. Because otherwise everyone would just have to invent mathematics for themselves, and it would be all fragmented. It's like Carl Sagan said in his book. He said the reason human beings have intelligence is they were able to collect libraries and consult them. Not because they have to remember and can't forget, or can't forget and have to remember, but because it's possible to absorb learning and share these derivations in the common language of mathematics in the symbolic form, as we've been talking about, and the notions of the deconstructive and this and that. So you might ask yourself, well, those are the two tools of classical construction, and And then there's stuff like some pegs and some string. What's this third tool of classical construction? Now there's something that's pretty cool. It's called the Archimedean spiral. And what it is you start at the origin, you draw a spiral, and how it is that every time it makes one revolution, it's one further out. And so when it makes the second revolution coming out of the spiral from the center, it reaches 2 on the x-axis, and so on to 3, and so on to 4. Well, that's called the Archimedean spiral, and there's a particular way that the curvature grows, and it kind of is as whether it starts as at a straight line upward from the origin, or as if it starts as a curve. So anyways, with one of those, then it's possible with compass and edge to square the circle. And various other things that are requiring a unbounded means otherwise, that just according to geometry make for closed forms, because that very thing, it closes it up as a form. Just like any made good, like a clock, a mechanical clock driven by springs, just by the configuration of how it's put together, is as of a model of an object that keeps time. Just like line drawing is a notion of a uniform abstraction, of a uniform act, of a uniform motion of continuously and infinitely divisible time at a stroke. That the stroke is in logic what they say decides things. That at one stroke you're able to line up a model and then draw through it its line and arrive at that what is arrived at, or eliminate that which is eliminated. So then the other notion of squaring the circle was from reading the dictionary of symbols the other day. It has an interesting context about squaring the circle, because when you look at the coordinate plane, is it a square or is it a circle? On the one hand, according to perspective and projection, it's square from the outlet that makes a square lattice. On the other hand, it's a circle. There's any ray you can draw from the origin of the same length only draws a circle. This is where the ray is kind of the ray has a beginning and no ending, and whereas a line has no beginning and no ending. That a line is that any 2 points defined through them in Euclidean space a single unique line. So a ray then helps define what is a circle. But there's many other things that can make it. And not just like how an octagon can be drawn in a square by chopping off the corners, and you could kind of iterate that again as another example of a way to arrive at circles within and without other geometric forms. That these are tools that together make up for methods. The methods of classical constructions compared to these symbolic methods, which admit models that are the same things. That most of these methods of algebra also have a model in geometry. This is like when Thomas Hardy says in Pure Mathematics that real numbers and the points of geometry are about the same. It's that they model each other. And then that there are multiple notions of this continuity is a pretty great thing, important. So I suppose in these talks, we didn't talk about differential equations and differential geometry is about these submersions and these beginnings of methods. One thing about these is that some of them leave off. So like some of these will make for closed forms and finite systems, and then make it so that they're still kind of general on the outside. This is that to get to the completeness part, the quantum field theory is like quantum field theory is a continuum mechanics. We actually need the degenerate and the outsides. It's got to be more general. And then the different equations with these symmetries is just an example of a way to find that there are some systems otherwise intractable which can be closed and solved. So many of these contributions, nonlinear partial differential equations, are like, well, these are all sorts of things that end up being nonlinear ODEs, and so we try to solve them at least in one direction called partial, and then insofar as that could go and how that would be, that it ends up that there are lots of these different ways to go about that. And so I guess this is more talk about the differentiation and the differential. with regards to the circular and all that kind of stuff. Because otherwise we've been talking about the path integral, and then some talk about deconstruction in the analysis. Then this probably pretty much falls under the analysis, the standard and non-standard analysis. But it helps to reflect that all the things that come together from the differential analysis kind of see that they emerge as acts of line drawing, classical constructions of geometry from the one side. That this is the other side that's attained to by all these classical constructions that fills in so much. Here I have this book, and it's called A History of the Circle by an Ernest Zebrowski Jr. As for the waves at the beach, in the distance they are a chaotic chop. Closer to shore they rise as a series of undulating crests and troughs, and at the surf line they explode into chaos once more. Equations can be written to describe, at least approximately, all of these effects, and ultimately such equations turn out to be based on the geometry of the circle. But do we actually see such circles when we watch the surf? Yes, if we pay attention closely enough, we not only see the circles, but sometimes we can actually feel them. Now, I enjoy that. It's from the preface, and he helps me appreciate my Platonist ideology, where Plato basically was able to accomplish the rejection of the fact that geometry is closed, because everything's subjective. Basically has it, there exist models of circles abstractly of us. Their ideals are Platonic ideals. Anything that it has a model, regardless of the non-logical, is a Platonic ideal. That we arrive at geometry and all this, if not necessarily by the most unique course yet, because we're interested in all the ways that it's real. And so I kind of appreciate that this year. Makes it so even the notions of circularity and for the recitative and oscillating and this kind of stuff, that when we talk about as he begins the book, this book is about something that doesn't physically exist, yet metaphysically it exists, and it exists as a concept, and it's enduring, and it exists. And so what I'm curious is to find some things about it. He describes the ratio, or the constant that is pi, circumference over diameter. We could talk about numerical coincidences and 22/7, and here's described the historical progress in determining the value of pi, that these days pi's digits, according to digit extraction algorithms and spigot algorithms like the famous, not Bailey and Borwein so much, but Plouffa's, P-L-O-U-F-F-E, Plouffe provides a closed form formula to determine the nth digit of pi. That's remarkable. If someone, I saw that, I was like, no way can an irrational number be represented as such in a closed form, each of its digits. But it seems to be so. And he describes that n goes to infinity, that an infinitely sided polygon is a circle, or that only has one side. And when you think about it, a triangle has three sides. There isn't really a polygon with two sides, although you might consider just a line the polygon with two sides, and then the circle is, as of that, only being one side, but at the same time now it has an entire inside or something like that. Anyways, these are the kinds of ideas that get into matters of projection and perspective that help establish for analysis that it, besides the square root of 2, because there are straight lines and there are right angles, that the square root of 2, according to Pythagoras, is the value of a hypotenuse of a right triangle of an isosceles triangle with the right angle at the equal sides, of course, that it works out that then these sine and cosine functions about Pythagoras and the circle build all kinds of the quadrature, because it's got 4 quadrants, and it's got the simple sine reversals plus minus in each of the 4 quadrants, those functions, which also happen to draw the sinusoidal wave, which can also be drawn by taking an equilateral triangle unhinging one of its corners, and then tracing out from it the path of that corner as it sweeps through a curve, that each of the triangle's sides as hinges open at the same rate. It's so possible to draw sine and cosine like that, besides as of a drawing it out as the circle rolls around with the computation or drawing of sine and cosine as within the that sine and cosine are orthogonal functions about circle. These notions of the symmetry and the reflection and the oscillating and the periodic built up about that end up being that it's a really natural form, that it's irrational, but it's also called transcendental, that pi is a transcendental number. So before even, at some point, it was agreed that there are only rational numbers. And someone suggested, well, root 2 is irrational. And as the schools evolved, it got to where that guy either was on the boat or not on the boat. And then it got to where, okay, root 2 is not rational, because there are very ready proofs that root 2 is not rational, because of the fact that if it were, then there'd be another one, and so on ad infinitum to regress, ad absurdum, as it were. But pi is in the time before any other irrational quantities existed, that root 2 at least is still algebraic, it's the root of an integer. Pi was an irrational number that was transcendental. So then there are some ideas that pi existed in these numerical systems before other irrational numbers, where any irrational number that's not an algebraic number is called a transcendental number. And there's a guy named Mahler, Mahler, and he has various kinds, for example, of ST and U transcendentals about various existence of definitions of them. And there's various ways to look at the Kolmogorov complexity, and about the Sierpinski and Gödel's complexity of what it takes to make certain classes of transcendental numbers. That here, it's also a ratio, and it ends up being usually is divided in terms of a number that's highly composite, like 360, so that 2 pi radians, which is a dimensionless quantity, and 360 degrees is a dimensionless quantity. They used to have what's also called the gradients, which is 400 gradients. There's 100 in each quadrant, and that was used in some domains because it was kind of about the square inside the domains and root of 100 for each one of those. So 400 gradients and 360 degrees and 2 pi radians are these going about the circle. And it was usually defined so that for very particular ratios of radians, like a quarter or a third, and those represent certain particular 30, 60, 90 triangles, or 45, 45, 90 triangles, that when drawn on the curve have certain particular values as for their sine and cosine, like root 2 over 2 and root 3 over 2 with respect to Pythagoras' theorem, and interpolating among those numbers, which is so great. Another thing, harkening back to the Archimedean spiral. It's a spiral, and then it's so that each revolution it increments exactly 1 on the outside, compared to like a conch shell, which grows out according to the golden mean in so many cases. Another irrational number, but found everywhere. Root 2, pi, the golden mean, natural logarithm. That if you draw a parabola, it intersects various integer points like 2 squared and 4, 99 squared, or 100 squared, and 10,000. So if you connect all those integer points on the parabola as they cross the axis, it crosses all the composite numbers and does not cross any of the prime numbers. That, when I first saw that, I was boggled. Because how can it possibly so be that the simple matter of quadrature explains the distribution of the prime numbers according to having closest form? that if we had a parabola and you needed to detect a number, you could fly out in that parabola to an integer point, or rather fly along the axis and see if any lines of all those integer points met it. Because you only have to go so far up the arm of the parabola before you could determine for a given number whether or not any one of those lines had intersected the axis, and thus it was prime or composite. It's an indicator to be read off without, for example, trial division, the long way, the general way. Can you determine how if a number is prime or not, that it has only two factors and only one factorization, and those numbers are one in the number itself that is prime? Yeah, you can try to divide it by every number less than its square. You don't have to divide more than that, because by then you've tried enough that its other factor would be above it. So anyways, this is another good example, like having another tool, although it's pretty much impossible to hand draw an Archimedean spiral, and it's pretty much difficult to make a parabola with arms that go out, a million billion times past what you want to count to. But if you have one, it still provides closed form solutions for all these things. So I've gone adrift a bit from talking about the quadrants and, for example, only the positive numbers. Or let's talk about only the positive numbers and the principal and non-principal square roots, because negative numbers squared are also like that. Or, well, we'll talk about revolutions and periods, and as there's a course of passage in uniform time about a circle, that it defines the correspondingly these values that can be interpolated for the sine and cosine functions. And it's in terms of the tangent function is the hypotenuse. And then with regards to the tangent, then it was like, well, how is a tangent the same thing as a tangent line to a curve? And what does that mean in terms of why are those named the same? Can't really tell you. But it is so. So this book goes on to describe various infinite series that evaluate to equal pi, that make it so that, as he puts out, it turns out that the fractions in the series shrink sufficiently quickly that their algebraic sum converges towards a fixed value, which happens to be pi. Unfortunately, those particular series is not an expedient method for finding pi, because even after 300 fractions are summed in this manner, the answer is still accurate to only 2 decimal places. Then the author gets into the irrationality of pi. As we expressed before, it's irrational, but at the same time it's transcendental. And so its value is able to be derived from these other geometric figures that via other means might be so available. In this case, that whether pi or 2 pi is the natural thing for pi times diameter, or 2 pi the radius, they're called radians. It's about the radius. And then as with regards to the diameter and the diopters and that kind of stuff, is that they're different branches of analysis. Branching out from analysis is about the circle, and so some of them depend on the diameter and some of them depend on the radius. That it's a little bit more general and usual that all the forms are in the radius, because then in terms of otherwise being the diameter, we have half the diameter everywhere. And while that is so, it's most well known that the length of the circle, the path integral, the line integral of the drawing of a circle whose points are equidistant from an origin each, 3.1415927.625, or pi. Or here, he's got one, pi, 3.14159265358979328. Oh, excuse me, 3238846, da da da. They have contests in memorizing the digits of pi, and there's some fellow who read out thousands and thousands and thousands of digits of pi. They have a number, they compute pi, and there's one place that has like 50 megabytes of the first digits of pi, or more. Billions and billions of digits of this irrational number that never repeat. What distinguishes pi from root 2, then, does not lie in their actual patterns of digits. The important distinction is the fundamental definitions. Pi is the ratio of the distance around a circle to the distance across, while root 2 is the ratio of the diagonal and square to the length of its side. The power of working with irrational numbers does not derive from their specific numerical values, which can never be expressed exactly anyway, but rather from what those numbers mean. By transferring such meaning from abstract definitions to the real world of physical objects and processes, we can often gain tremendous insights into the workings of nature. So then he gets them talking about rollers, wheels, and bearings, and this is a funny one because when you look at the circle and consider it rolling around, and then you consider the circle that's within it, and they share the same axis, but that as one is rolling around, then the other one only rolls around in revolution too, but its center is dragged along the same way. So on the one hand, the inner circle has gone less distant, but the outer circle has gone the full distance, but the center of the inner one has been pulled along more, whereas the center of the outer one is just rolling. It's like so for the infinitely many circles within a circle. A circle is the set of points equidistant from the center. A disk is all the points within those. Any set of points less than or equal to all those. And he talks about rollers as wheels and transporting heavy blocks as of on multiple rollers, so that then basically you can roll something along some rollers, and then as the roller behind gets left behind, you pick it up and place it in front again, and then you roll over it again, and then use the fact that the wheel is one of our simple machines, and knowing the simple machines is a real key thing, like the lever, the wheel, the inclined plane, the screw. There's 5 or 7 simple machines, and they're very well known, and everyone should have an idea of what kinds of mechanical advantage they provide, in the sense that basically if you have a wheel, it does not, except for the stresses on the axis of the wheel, it is frictionless. And it's how railroad cars, for example, or steel wheels implement a multimodal transport infrastructure. So this book is kind of interesting, and then he describes, for example, what happens if you roll a spool around a wheel and then pull it up, so thus as you pull it up, you're slowly gaining on it, because as it unrolls the wheel, you're pulling it up the inclined plane or ramp. He just describes the inclined plane as the ramp. Thus, the total length of rope that has unwound in one revolution is pi d plus 2d root 2. Again, this leads us to a constant ratio situation. Effort distance over load distance equals equals 1.9. So here he gets into what would be other derived constants and quantities that maybe those are the real constants. That other stuff, how the circle emerges from these processes that can attain to it, how they're maybe degenerate from what then arises as to the generate or the generative, that there are other transcendental numbers that you can read off from any point of the development, and whether that development's reversible, and arrive at, particularly if you can arrive at other transcendental constants. Like, how do you relate E and pi? No, they're two different things. They're for two different reasons. How do you relate root 2 and pi? Well, there's a couple points on the circle about sine, cosine, but no. These transcendental functions do not have ratio to each other. Although there are what's called numerical coincidences. Numerical coincidences are where two irrational numbers so happen that even at a particular high order of precision, that for a particular low level precision of a ratio, that they're equated in a very high precision. Like the 22/7 is often given an example. As far as you crank that out with long division, it's pretty close to pi. But these numerical coincidences are even closer, and really get into where then it makes it, for approximating terms, sometimes much easier to read that off tables and compute those out, His chapter 3 reads, The Celestial Clock. And he describes tumbleweeds and A fish snatching a fly from the surface of a still lake sets off a series of circular ripples that expands outwards from the point of the disturbance. Pebbles and streams tend to get worn into roughly circular shapes. He mentions tumbleweeds. The other day I was driving across the country, and this is an area which is some rolling hills, and the road is basically up above it, so it's an area of farmland, and it's dirt farm, And what that means is that it's irrigated or so, or maybe it gets rain. It's not a dry farming. So anyways, the other besides the crops, then the other natural or current plant there is tumbleweed. And tumbleweed is a form of sagebrush, and how tumbleweed gets around is every year it's like a perennial or an annual plant. So it's kind of like an annual, and it grows a tumbleweed, and then it dies, but then the tumbleweed rolls in the wind and flies off to where it lands, and then its seeds are dispersed, and then the wind carries along. It's a tumbleweed. So at given times of year, you can drive through this part of the world, and the road is full of tumbleweeds. There are piles of tumbleweeds everywhere. The tumbleweed is flying around, and it's basically lucky that tumbleweed, as it flies through the wind, is not so much that the car's motion is stopped by tumbleweed in the road. So anyways, I came over this rise, and what I saw in front of me, I'm not unused to seeing like dust devils or dirt devils, which are small cyclones that have a bunch of dust, or tumbleweeds just blowing around. But it just happened that it was a really spherical ball of tumbleweeds, like about 200 or 300 feet across, but they're mostly, at the outside of this ball, that I'd never seen like ball cyclone before. I've heard of ball lightning or something like that, where lightning is a stroke from the sky that is an arc, and ball lightning is a form of a charged cloud or something like that luminesces. But this ball cyclone of the tumbleweeds is something I hadn't seen before. And I thought that as to its formation was kind of contrived. Wheels in the heavens. The author talks about Mesopotamia and Egypt, Cassiopeia, the Big Dipper and the Little Dipper. Talks about the moving and non-moving stars. The planets called the travelers, the stars. Of sixes and 60s, he begins to introduce that 360 is a highly composite number because 12 is so abundant. An abundant number is the sum of its factors is more than it, that it has many ways to factorize it, so you can get it even at a bunch of different ratios, 1, 2, 3, 4, 6, or 12. And for 12, for example, it makes it so that abundant numbers are highly factorizable, and they have many factors compared to the prime factors have 2. And so these abundant and highly composite numbers, like 360, are used in the ancient mathematics, especially, that it was the standard base or representation of numbers, because as a fraction it could be broken down that way, and also there's so many ways. And it was close to 360 days a year also for the calendar. That is 365.25-ish days per year. And from that we get minutus and secundus, minuta and secunda, minutes and seconds, the hours, or well, I'm wondering then if this is I imagine is about analysis, because in a sense it's about just some fundamentals of transcendental analysis, and the fact that there are classical constructions and tools and methods and what enclosed in general forms, and there are others, and that all this is applied generally. Here he's just describing that a lot of the Swiss went into astronomy for the calendric. The calendric is that there are two kinds of time. There's calendar time, which is days, and there's clock time, which is minutes. And that they add up, that it goes around a clock modulus every day and restarts that time is similar to that in other methods of timekeeping. We can say that our epoch is January 1st, 1970. That is time 0 at midnight, times 0, hours, minutes, ... 0 seconds. And that every day since then is the day since the epoch, and every minute since then is a minute since the epoch, and every second since then is a second since the epoch, and every millisecond, nanosecond, since then is a millisecond or nanosecond, respectively, since the epoch. Vis-a-vis that it's simply not so, that each day is 86,400 seconds, so the 24 times 60 times 60. There's a little bit of give and take in the cosmic clockworks, That, though, it so arrives that in what we have what's called universal time coordinate, or coordinated universal time, UTC or CUT, and it's based upon Greenwich Mean Time, or Greenwich, England, is an observatory, and where it is where there's this place called the Prime Meridian, and the meridians about the Earth, as about the longitudes, are in terms of split into 24 of those about the Earth, and thus that it results then opposite that about is what's called the international date line, that on either side of that is the day before and day after, as it were. And thus the results that the constant clockwork timekeeping and the overall revolution of the Earth, as the sun rises and sets each day, has that there are not necessarily 86,400 seconds per day. But it is so that each day is computed as the days since the epoch, and then the seconds in that day since midnight are one of 86,400 seconds since the beginning of that day. And thus we have a regular modular timekeeping apparatus in terms of then that the coordinated universal time is pretty much in terms of that there are corrections, and that otherwise Zulu time is UTC. Terrestrial. So Pythagoras was born on the Greek island of Samos around 582 BCE. That's before Common Era. It used to be written before Christ, and now it's written BCE, before Common Era, and he died in 507 BCE. And it used to be written Anno Domini AD for since 0 AD, and now it's written since 0 CE, a Common Era, which can be considered an epoch for the calendric. That the epoch January 1st set 1970 is usually at the timekeeping in the modern 21st century computer worlds, and these days there's some idea that make that January 1st 2020 instead, which is 50 years or 18,262 days since January 1st 1970. Pythagoras. We know nothing about the man's writings, and it's quite possible that he never wrote anything. In ancient times, it was common practice for great thinkers to delegate the documentation of their ideas to their students and followers. We do know that the ideas and teachings of Pythagoras attracted a large following, and that his students developed a religious society that survived for a century or two after his death. So we can think of Pythagoras as a kind of panel again, and a school of men. These Pythagorean disciples contributed numerous writings, some profound, some apocryphal, meaning not necessarily reflecting that which can be found, mystic, but as well related and rumored or to exist, and some, unfortunately, ridiculous. Compounding the confusion, only fragments of many of these documents survived through the ages, often after going through numerous transcriptions and translations that may have resulted in various embellishments and omissions. Regardless of the confusion about the details, however, it's clear that Pythagoras didn't originate a tradition that has had a profound influence on Western thought, the tradition that mathematics can uncover fundamental truths about the physical universe. Pythagoras was preoccupied with the question of whether numbers and mathematical logic have anything to do with patterns and order observed in nature. Not only did he observe the natural world around him, but he also tweaked it in various ways to see if it spoke back in a manner that could be interpreted mathematically. In one of his experiments, he took a multiple-string musical instrument and strummed a note on one string, then he tuned a second string so it sounded the same musical pitch. Next, he placed a movable bridge onto the second string and slid it along the string's length, carefully listening until he located points that were in musical harmony with the unbridged string. When he found such points, he compared the length of the bridged string with the unbridged string, and he expressed this relationship as a ratio. Ratios delivered a big surprise. The strings sounded in musical harmony only when their lengths were in the ratio of a common fraction. Now, there's nothing strange per se about bridging a string at half its length, 1/3, 1/4, and so on, any more than it would be strange to cut a loaf of bread in 1/3 quarters. But unlike the bread, the vibrating string speaks back. So this is an interesting foray into musical theory, that there's tone, there's fundamental tones, there's also overtone, and about the constructive and deconstructive and the acoustic, and the linear and the nonlinear and the acoustic, and the important value of overtone, and for me, in my usual perception, the significance of destructive tone, which results higher order harmonic frequencies, which are composite tones, and overtone that are harmoniously pleasing and reflect, regardless of scale, fundamental relations in tone. And what this string seems to be saying is that it prefers to be bridged according to some common fractions because otherwise it produces disharmonious sounds. This finding intrigued Pythagoras. Fractions, after all, are but an abstract creation of the human mind. Why should fractions have anything to do with physical musical instruments unless the products of human mathematics and the workings of the universe are intrinsically intertwined? Well, this is nice, and it leads one to think also of the Platonic ideals. And Pythagoras is essentially, besides being a Platonist, also starting to be a strong Platonist. That, yes, these numbers and abstractions are free from us, so leave them alone, you poets, and then bringing it back and saying, furthermore, they're strong in here, again. And then Pythagoras is so important for his ratios. Going back to the story about being in or on the boat, or offer on the boat, the idea was that there's a story, an apocryphal story, that says that the Pythagoreans were on the boat. And so one of the Pythagoreans, or variously one of the ones who wasn't Pythagorean, said, the root 2 exists, and it's irrational. And the other Pythagoreans, who accepted only the rational, threw him off the boat. Then whether he drowned or whether he was just excluded in a strong sense. But then the other idea is that the story also has a historical example, and it was that really the guy was thrown off the boat for giving away the secrets of the Pythagoreans. That the Pythagoreans would have, for example, this exoteric teachings, which is rational, is Pythagorean, and it's harmonious and pleasing. And then these esoteric teachings, which are like, these are not what we have publicly, but they are true for us, but they contradict or are not complete, or we can't vouch for them in terms of our exoteric teachings, that they are esoteric teachings. Or that they're esoteric teachings like, this is our real truth and how we keep things constant, and that otherwise there's a difference between the inside and the outside. So anyways, somebody said something and there was big trouble. The followers of Pythagoras embraced this idea as axiomatic. The essence of the entire universe lies in mathematical patterns. There are transcendental mathematics and non-standard mathematics. There's infinity. There are patterns. So anyways, this is a pretty interesting book, and it kind of helps to build a history of these things. Ultimately, when they began to interfere with traditional religious customs, the Pythagoreans were driven out of Greece. Because they tried to explain that they were strong mathematical Platonists, that was their strong mathematical god, or not that it's okay to have mathematics as your religion. It's just that for some people it is not. And that's okay too. So, and then it gets in a bunch of different developments in history, and it's useful. It provides a context to somebody who's spent a lot of their life thinking about mathematics and about how it relates to the world and a worldview and a vision of history and a universal history. And then he describes in the mathematics and the physical world the rise of formal geometry. So by 300 BCE, it was apparent that many geometrical relationships could be described exactly, or in the closed forms, exactly in the abstract, provided one pretended that physical constructions and their measurements were exact, or made them precisely enough that one could not find them any different. Then he mentions Euclid, and then we've already discussed Euclid. That Pythagoras is a panel, and Euclid is a panel, Bourbaki is a panel, and they represent very strong concepts in mathematics, or less so if you count Bourbaki, which is about 2,400 years later. So there's quite a bit to be read from that. This kind of history of the circle, history of the conceptual development of the concept of the circle, a history of the thinking about the transcendental, a history that includes the tools available over time, that all the proofs that have ever been valid are still valid today and ever will be. Although one might argue that where that metaphor ends, because metaphor fails eventually, and there's a strong metonymy, but metaphor eventually fails, is that sometimes some things are axiomatized to be proven unique, or axiomatized what is so. That is a decision, that is a choice, that is a rule, that is a stipulation, that is an assumption, can be negated. Then when we get into sometimes what are called uniqueness results, sometimes there are so as in accords with these things, but there may be other solutions, other forms that help or do arrive at these same means, the same methods, different techniques, same objects, or equivalent objects, or that there exists the extensionality is about relating the models of the objects. That gets into why, as we began this discussion, that Peano's notions of the successor function is pretty much unique. The notion of a set defining membership by its elements is pretty much unique. It's one relation. It's agreeable that in any model it's about the same. But any structure they build up maybe so is about any operator or operator calculus about them, finite or infinite. And so when it comes to that, the analytical character of 0, 1, the unit interval, can be built up long before you find Galois theorems in group theory and the usual standard development of real analysis up to making a formal description self-contained after axiomatic set theory that axiomatizes an infinity, a set containing each ordinal less than that doesn't contain itself, which is a stipulation. It's not unique among possible interpretations. Then it so follows that as well they come back together. They're both strong derivations, and for bringing them together. So all right, I suppose then again this is again about analysis and models of analysis and the analytical and the deductive, and the synthetic and the analytical. That without pretty much saying much, it's fair to say that without much further ado, that for Zeno's paradox, that the archer's arrow goes halfway and then halfway and then halfway there again, so it never arrives. There's that you can instead have each of those ones on either side a piece, and so it never starts or never arrives. And then for each milieu through which it crosses, it never enters or leaves, nor does it spend the same time in each. That it does, and then that's constant uniform motion between 0 and 1, and it's a model of constant uniform motion, this line drawing, a fundamental primitive before geometry. And then for Hardy's pure numbers and pure geometry, this model that's the same for both of them somehow, it's not so far-fetched to arrive at that then before even reading Euclid's axioms and elements and being able to employ fully all his tools of the classical constructions. We can arrive at the tools abstractly, cognitively, from not much else, from nothing. So in that sense, it kind of reflects this talk about how does it arise anything from axiomless natural deduction. In another sense, it kind of arrives at like, how do we implement analysis? That did the same thing. Well, all right then. You know, and then with regards to how probability works and theory of probability and how cars work and how globe cyclones work, apparently. and excessive functions for a class of continuous time Markov chains, Dinkin diagrams and such. And that for continuum mechanics, it's a continuum mechanics. Well, all right then. Hey, have a great day.